This worked example uses a combination of 2D and 3D methods to understand and optimize a virtual library of heat shock protein 90 inhibitors. The library, created by a de novo design process, is based around an amide substitution on a beta-racinoic acid core. The objective in this example is to use the SeeSAR module to develop an understanding of the 3D structure-activity relationships, and then use multi-parameter optimization to further develop the absorption, distribution, metabolism and excretion, as well as physicochemical properties of a potent inhibitor without losing efficacy. In StarDrop, open the project file HSP90 Virtual Library by selecting Open from the File menu. You'll see a spreadsheet containing 124 structures with their estimated affinities for HSP90 displayed in a histogram. StarDrop enables you to look at your datasets in a variety of ways, and we can switch between views of our data at any time. Card View provides a flexible environment for exploring the relationships between compounds because we can move, stack and link cards to organize our ideas. Click the Card View button on the right-hand toolbar to switch into Card View. To begin understanding the SAR within this virtual library, we're first going to perform a matched pair analysis. Using this approach, we can identify whether there are any small substitutions on otherwise identical compounds which result in a large change in the estimated activity. From the Analyze menu at the top of Card View, select Find Matched Pairs. The dialog that appears enables us to define the results we would like to see. For this example, we are going to use all the default settings it suggests. Click the OK button to start the analysis. When complete, the results will be shown in a Card View network where each matched pair has a link between the corresponding cards. A table will also be created showing a summary of the matched pair transformations, the individual matched pairs, and a histogram displaying the distribution of changes in a property value for the matched pairs. We can use the matched pairs table to identify the largest variations in activity between pairs of compounds. In the matched molecular pairs window, click on the header of the delta hide column twice. Each time you click on a column header, it changes the sort order between ascending and descending. By clicking twice, we can sort the table in descending order. In the first row, we can see that the change from the N-acetyl derivative to the hydroxymethyl piperidine derivative has resulted in a large change in the estimated activity. Select the first row in the table to highlight the pair of compounds in the dataset. You can zoom in and out of Card View using the mouse wheel or the Control and plus and minus keys. If you hover your mouse over the link between the two cards, a pop-up will display them side by side. To investigate what might be causing this big difference in estimated activity, we can look at the 3D compound and protein structures. Close the Match Molecular Pairs window and click on the SeeSAR tab at the top. The PDB file 2xjx has already been loaded into this StarDrop project. Below the protein you will see a table which contains 3 ligands. The first is an alispib, an HSP90 inhibitor which was included in the PDB file. The other 2 ligands are the pair we selected in Card View. Any ligands we select in our main dataset will be available in the table below SeeSAR for viewing in the protein. Select the second row in the table below SeeSAR. This is the ligand we identified with good estimated activity. Now click the Show Binding checkbox above the protein to change the view of the protein to focus on the binding pocket. Using the mouse you can interact with the view of the protein. Use the mouse wheel to zoom in and out, use the left mouse button and drag to rotate the view, use the right mouse button and drag to pan the view. When you choose the Show Binding option, hydrogen bond interactions between the ligand and protein are displayed by green dotted lines. Focusing in particular on the hydroxymethyl piperidine portion of the ligand, we can see its bidentate interaction with HSP90. Click on the bottom row of the table below to display the N-acetyl derivative instead. Here we can see that there are no equivalent interactions between this part of the ligand and the protein, which suggests that this may be responsible for the significant reduction in the estimated activity. Having considered some of the reasons underlying the estimated activity of the ligands in this virtual library, let's take a look at some of their ADME and physicochemical properties. Change back to Table View by clicking the Table View button on the right-hand toolbar. Click on the Models tab at the top of the main StarDrop window. To run all the StarDrop models, click the checkbox next to the word StarDrop to select all the models under this branch, and then click the Go button. When this process is complete, you'll see that a new column has been added to the dataset for each property calculated. Due to the volume and complexity of the data, it is challenging to find the compounds which have the best balance of properties, and so we're going to use StarDrop's approach to multi-parameter optimization, called probabilistic scoring, which will make it easy to assess all of this information together. Click on the Scoring tab. A scoring profile enables you to define a set of criteria that are important for your project. StarDrop has some example profiles built in, and for this project we have already created a profile that can be used to assess compounds that need to be active against an oral, non-CNS target. Click the Go button to run this scoring profile. A new column will be added to the dataset containing scores that indicate how likely each compound is to be successful against the profile of criteria given the data available, taking into account the confidence in any predictions or measurements. Change to the visualization area. Click the Detach button to create a new dashboard containing the histogram. Note that any other charts you detach will be added to the dashboard, which you can organize and resize by dragging plots and the boundaries between them. In the dataset, select the score column by clicking on the column header to generate a snake plot. A snake plot shows the scores for a whole dataset, ordered from highest to lowest, indicating the actual scores along with a confidence in the scores due to the uncertainty in the underlying data. All of the data in this set have been predicted, which is why there are a lot of large error bars. However, there are still significant differences between the highest and lowest scoring compounds. In the histogram, click the bar which contains the compounds with estimated pKis above 8. Any selections you make within charts or datasets in StarDrop will always be reflected everywhere else, so we can quickly see from the snake plot that the two most potent compounds have very different scores. Let's take a closer look at the properties and the reason for the low score. Note that the two rows are also highlighted in the dataset, and you can see that the ID of the lowest scoring compound is row 3. Close the dashboard. Change back to Card View by clicking the Card View button on the right-hand toolbar again. Card View is still showing the matched pairs network we created earlier, but we can easily change this view. Click on a space somewhere between the cards to deselect everything. Zoom in to make the cards a little larger using the mouse wheel. Click on the Link button to show the link tool, and then click the Remove Links button to remove the network. Now select Grid from the Layout menu at the top of Card View to tidy the cards into a grid. Finally, click the Hand button at the top of Card View to change back to the general mode in which we can move cards around. The cards only show the compound structures and their estimated activities, but we now have ADME and physicochemical properties in our dataset, as well as a score for each compound. We can use the Card View designer to customize the cards so that we can compare multiple properties simultaneously. For this example, there is already an alternative card design saved as part of this project, which we can use. From the Design menu at the top of Card View, select User Designs and then HSP90 Score. In Card View, zoom in to look at the properties of the second compound, called row 3. In the scoring histogram, we can see that the two lowest bars, which indicate the potential problems, are the cyan and pink ones. These correspond to log-P and hERG-P IC50 respectively, and the values of these two properties are shown below. When scoring the compounds, we indicated that we would ideally like a log-P value between 0 and 3.5. We also indicated that an ideal hERG-P IC50 value would be below 5. StarDrop's glowing molecule highlights regions of the molecule that are having a significant effect upon a predicted property. This can help to guide the design of new compounds by indicating regions where a small change in structure may have a significant impact on the predicted property. Click on the log-P prediction on the card to activate the glowing molecule visualization for log-P. Regions glowing red are tending to increase the predicted value, whereas regions glowing blue are tending to decrease the predicted value. Now select the hERG-P IC50 property to view the glowing molecule representation for this prediction. For both the log-P and hERG-P IC50, we can see that regions around the beta-raciocylic, phenyl and pyrrolidine rings are red, indicating that these parts of the molecule are contributing to an increase in these properties. We can now easily compare the 2D SAR indicated by the predictive models with a 3D SAR indicated by the docking pose. Change back to the SeeSAR area and you will see this compound shown in SeeSAR. From the display menu at the top of SeeSAR, choose Protein, Surface and then Show Surface. Rotate the structure within the SeeSAR area to see how the ligand fits into the binding site. Whereas the raciocylic acid core sits deep within the pocket and forms a strong hydrogen bonding network with the protein, the phenyl and pyrrolidine rings sit outside the pocket, showing no obvious strong interactions. This suggests that these regions may not contribute strongly to the compound's binding affinity, so these rings may well be a good place to consider making modifications in order to mitigate the risks of high log-P and hERG inhibition without having a large effect on activity. we can use StarDrop's interactive design tool to explore the impact of possible changes. Change to the design area. Here we can edit and design new compounds, and the selected molecule, row 3, is already shown. Below the molecule editor, you can also see predicted properties which will update as we modify the compound structure. Click on the Bonds tool and add a carboxylic acid at the meta position on the phenyl ring. While editing the molecule, you'll see that the properties below the design area will update to show new predictions for the displayed molecule. If a property in the list is selected, then you can also see the glowing molecule for that property update while editing. The carboxylic acid derivative has a log P of 3.26 and a hErg PIC50 of 4.6, and so this compound would appear to have a better balance of ADME properties. You can see all the other properties as well to confirm that none of these have become significantly worse. Add this new molecule to the dataset by clicking the Go button. We could continue to investigate other alternatives, and to find out the effect any changes have had on the predicted activity, we could use StarDrop's pose generation interface to link StarDrop with your preferred docking program to generate poses and score the resulting fit to the binding pocket. The pose generation interface is not covered in this tutorial, but for examples of this, and StarDrop's many other features for selecting and designing compounds, take a look in the Optibrium community.